Hello, in this video we're going to be talking about the Gen Chem review to start organic chemistry. A lot of you probably about to start taking organic chemistry, so you want to make sure you know some of your general chemistry stuff before you take the organic chemistry. So in this lecture we're going to summarize everything that you need to know about the Gen Chem before you take organic chemistry. So I'm going to start out with electron dot structures, also called the Lewis dot structures, which is basically the representation of the valence electrons around the element and around the covalent compounds. So we'll start out with just the elements first. If I'm looking at aluminum, I want to go back and figure out in the periodic table how many valence electron aluminum has, and aluminum is actually going to be in group 3A. So here I have a rough representation of the periodic table. I don't have all the periodic table drawn here, and that's because you don't really use all the elements in organic chemistry. You're going to be mainly focusing on the elements that's in the second period, the halogens, and some of the elements like phosphorus, sulfur, silicon, and some of the alkali and alkaline earth metals. The rest of the elements not really used in organic chemistry. Maybe some of the transition metals here and there, but mostly we're going to be focusing on these carbon-related elements and these halogens. Now, if you have forgotten how you figure out the valence electrons, the valence electron is just going to be the group numbers with the alphabets there. So 1A, 2A, 3A, 4A. So that literally tells you how many valence electrons you're going to have. Your aluminum is in the boron family because right below boron you have aluminum. So this is going to have 3 valence electrons. So when I represents the 3 valence electrons around aluminum, all I really got to do is just put 3 dots around aluminum so that and make sure they are as far away from one another. The next one I have here is the chlorine. Chlorine is in group 7A, so that's going to have 7 valence electrons. So I want to go ahead and put 4 around the chlorine first, and then I want to go back and start pairing them up. So it's going to be 5, 6, and 7. So that's going to be giving you 7 valence electrons. Now, obviously, the most important element in organic chemistry is the carbon, and carbon is going to have 4 valence electrons because it's in group 4A. So I'm going to be writing 1 here, 2, 3, and 4 electrons around carbon. So that's going to be the basic representation of the electron dot structures for these elements form. But now you want to make sure you are aware of how to do the electron dot structures for the compounds, and especially we're going to be focusing on the compounds that contains carbon and maybe nitrogens here and there, but we're not going to be focusing on the compounds too much that are inorganic in nature. The first thing you want to make sure you know is the Octet Rules. The Octet Rule says whenever elements makes compound, whether it's in a covalent compound and even the ionic compounds, they try to have the electronic configurations the same as the nearest noble gas, or which another way of saying most of your noble gases except helium is going to have 8 valence electron. So whenever these elements makes compound, they would like to have 8 electrons at the end of the day. There are some rules on drawing the electron dot structures, and I'm just going to be briefly talking about those rules and drawing these electron dot structures quickly. But if you do need a deeper understanding on how to draw these electron dot structures, you may want to go back and watch one of my videos where I have strictly talked about electron dot structures in details. The very first rule is to find the valence electron. So since I have the CH4, the number of valence electrons would be, I got 4 on the carbon, and then I got 1 on each hydrogen, so that's a total of 8 valence electrons. And then figure out your central atom. Your central atom is going to be the carbon, and when I go ahead and write down the carbon at the center, and then I'm going to put hydrogens around the carbon, and put 1 bond between the central and the surrounding atoms. And before you do anything, you want to make sure you count how many electrons you have used. So remember, 1 bond is made of 2 electrons. If I want to redraw this particular one, I could also redraw it like this. I can have 4 hydrogens around the carbon and between each carbon and hydrogen there is going to be a pair of electrons, also called bonding pairs. But then you can also represent that in the form of a bond. And I did use 8 electrons, and that's all we had for the valence electrons. And then you want to make sure before you finalize your structure the octet is completed for all the atoms. So carbon does have 4 bonds around it, so that means it's going to have 8 electrons total, because all those electrons are being shared between the carbon and hydrogen. And hydrogen in each case is going to have 2 electrons, which is completely okay because the closest noble gas to hydrogen is helium, which only needs 2 electrons to complete the octet. Now, I do want to mention the 3-dimensional representation of this compound as well. Usually when you have 4 bonds, which gives you a tetrahedral geometry, you will have 2 bonds in the plane, something like this. So you got 2 hydrogens in the plane, and then you'll have one of them coming out of the page, and then you'll have another one going back into the page. So that's going to be the typical representation of the 4 bonds around the carbon when you deal with organic chemistry. So make sure you know the solid wedge comes out of the page and this dashed line goes back into the page. Okay, so since you have 4 electron domains around the carbon, the shape and electronic geometry for this molecule is going to be tetrahedral. And the bond angle is going to be about 109 degrees. And you don't really have to worry too much about the electronic geometries because shapes are more important than the electronic geometries. But in this particular case, if there is no lone pair on the central atom, then your electronic geometry and the shape is going to be the same, which is tetrahedral here. Let's talk about this carbon dioxide, and I got a couple of molecules here. I'm going to do those quickly, but it's going to be a good idea if you can pause the session here and do these electron dot structures on your own and see if they matches with mine. So I got CO2, so number of valence electrons in the CO2 it's going to be 4 coming from the carbons, and then I got 6 coming from each oxygen, so that's going to be a total of 16. And I can go ahead and put the central atom at the center, carbon at the center, and then I have 2 oxygens around the carbon. And then when you put 2 bonds around the carbon, that uses up 4 electrons, so minus 4, that leaves you with 12 electrons. And then what I can do, I can fulfill the octets of the surrounding atoms first by placing 6 electrons on each oxygen. And in doing so, you're using up all the valence electrons because 6 electrons on each oxygen uses up the remaining 12 electrons. Before you finalize your structure, you want to make sure everyone is happy in terms of the octet. But it seems like carbon has only 4 electrons so far because it's only making 2 bonds around it. And on the other hand, so oxygen seems fine because they all got 8 electrons. But to make carbon happy, what I have to do is just to use one of these lone pairs from the oxygens to create the double bond. Because sometimes you would have to create the double bond around the carbons to make sure the octet is completed. So this is how the actual structure is going to be for this carbon dioxide. Now this carbon dioxide has only 2 electron domains, and as a result it's going to be a linear in structure, and it's going to have 180 degrees as your bond angle. Okay, what about this NH3? We'll do the same thing. The valence electron is going to be 5 plus 3 times 1, so that's 8. And then I'm going to have nitrogen as the central atom, and then put 3 hydrogens around with single bond with one another. Now count how many electrons you used. So you used a total of 6 electrons because each bond brings in 2 electrons. That means you still have 2 more remaining. Anytime you have a remaining electrons, you want to make sure you use up those electrons to fulfill the octets of the surrounding atoms first. And then if you still have some left over, then you go on the central atom. But now in this case, the surrounding atom is hydrogen, and remember, hydrogen does not need anything but just one single bond, and it's already have it. So that means those 2 electrons will go on the nitrogen as a lone pair. Okay, so what's going to be the shape here? Well, we got 4 electron domains, so your electronic geometry would be the tetrahedral. However, since there is an alone pair on the nitrogen, your shape is not going to be the same as electronic geometry, and as a result, your shape would be trigonal pyramid. Since it's a trigonal pyramid, the bond angle is going to be a little bit less than 109. It's going to be around 107. So let's say roughly 107 degrees is going to be the bond angle there. So for tetrahedral, it's about 109, but since there's a lone pair, the lone pair is going to repel those bonding domains, and they're going to contract a little bit, so your bond angle goes down just a little bit. Looking at this HCN, the HCN is going to look like this. Okay, so again, around the carbon, you have a total of 4 bonds, and that's what you really need. But around the carbon, since you only have 2 electron domains, it's going to be linear in shape. And that's also going to give you an 180 degrees bond angle. When you look at the water, hopefully you have drawn the water molecule. The water molecule is bent in shape. It's got 2 lone pairs on the oxygen atom, and since it has a total of 4 electron domains, which it gives an electronic geometry of tetrahedral, however, the actual shape is going to be bent because of the 2 lone pairs, and your bond angle is going to be somewhere around 104 degrees because it's going to be even less than what you see in case of trigonal pyramid. So those are some of the most common shapes you're going to be seeing when you do the organic chemistry. Obviously, when you have learned electron dot structures in Gen Chem, he talked about octahedrals and other stuff as well, but those are not commonly seen when you take organic chemistry. So focus on these particular types, especially when you have carbon as a central atom. You could have nitrogen and oxygen as a central atom as well. Occasionally you may see the sulfur and phosphorus as your central atoms as well. Well, let's talk about some of the exceptions because they will come up at some point. The exceptions mean we talked about the Octet rule, and we said the central atom likes to have 8 electrons, but there are times when central atom does not have the 8 electrons, or another way of saying it has either less or more. So if it has less, it's going to be called an incomplete octet, and the compounds of boron are going to be the examples. Like I can have BH3, I can have BF3, or I can even have BCl3. Those are some of the compounds of boron, and even the compounds of beryllium sometimes are also considered to have an incomplete octet. Now, when I focus on this boron, suppose I have this BH3, and to go ahead and draw out the loose dot structure of this compound. So this is how it's going to look like. So clearly you can see the boron has only 6 electrons after the compound has been made here. And since boron has only 6 electrons, it makes the compounds of borons a little bit more reactive, just because it can have an additional pair of electrons added onto the boron. And as a result, these boron compounds are going to be acting as your Lewis acids because they can accept a pair of electrons. And they are also reactive because of that. Well, what if you have a central atom that has more than 8 electrons? Well, that can happen if your central atom is going to be from either third period or below. So some of the famous examples going to be something like PCl5, or I can say SF6, or I can talk about PBr5 or SOCl2. So all those are going to be the examples of compounds that has a central atom with exceeded octet. And that's completely okay to have the exceeded octet as long as you have a central atom from the third period or below. Now keep in mind your surrounding atom's always going to have 8 electrons except the hydrogen. So hydrogen is the only exception where it's going to have only 2 electrons at the end of the day, but the rest of the surrounding atoms always going to have the 8 electrons once the electron dot structure is completed. Let's talk about how you calculate the formal charge. Now, There is a fancy formula to calculate the formal charge, but when you take organic, you got to make sure you can quickly visualize how you can get the formal charge. And formal charge is just basically the difference in the valence electrons and the electrons possessed by that atom in the compound. So whenever they don't really match with one another, that's when you're going to have a formal charge. So for example, if I talk about CH4, and I know the CH4 electron dot structure looks like this. Think of this bond pair that's between the carbon and hydrogen written something like this. I got two electrons that are in the line there. And then each electron is going to be corresponding to the carbon in the bond, and the other electron in the same bond is going to be corresponding to the hydrogen. So if I draw the line here, you can clearly see how carbon has 4 electrons. That's to himself. And when you do the formal charge on this, in this particular case, it's going to be the valence electrons. So the valence electrons, that's coming from the periodic table, obviously. Carbon has 4 valence electrons. And then the electrons that are possessed by that atom in that compound. So in this case, carbon has 4 electrons again, so it's 4 minus 4, it's going to be 0. So that's the easier way to calculate the formal charge. You don't have time to write down, okay, bonding electrons, lone pairs, and all that. You want to be able to do those quickly. Let's look at maybe another example and talk about maybe water here. So remember, the water molecule looked like this. And we're trying to figure out the formal charge on this oxygen. We can clearly say the valence electrons in oxygen is going to be 6. That's coming from the periodic table. Now, how many electrons this particular oxygen atom contains in this compound? Now, if I draw in a square box here, think of the one bond is shared between the oxygen and hydrogen. So one of the electron of that bond is going to be belonging to the oxygen, and the other electron is going to be belonging to the hydrogen. So I have 2 lone pairs on the oxygen, so that's 1, 2, 3, 4. And then I got 2 bonds, so each going to be bringing in 1 electron again. So that's a total of 6 electrons, and that's going to give you a 0 formal charge. What about something like this? If I have something like this. We got nitrogen and it's surrounded by 4 hydrogen atoms. And if I want to calculate the formal charge on this particular nitrogen here, I know the number of valence electrons is going to be 5 for nitrogen. Now, how many electrons are being accessed by this nitrogen when it makes the compound? Now, I can go ahead and draw this little box here. So when you draw the little box here, then that just literally means you have 1 electron from each bond belonging to the nitrogen and the other electron from each bond belonging to the hydrogen. So you can, in this particular case, you can clearly see there is only 4 electrons on the nitrogen, so it's going to be 5 minus 4. Oops. So that's going to be a +1 formal charge. So this particular nitrogen has a +1 formal charge, and if you recall, there is an ion called an ammonium, and in that ammonium ion is the nitrogen that carries the +1 formal charge. So there's a couple of ways you can write this particular compound. I can write this as a nitrogen with a positive charge, or I can also write it as just draw out the whole molecule and write down the positive charge outside the brackets. So either one of those are fine, but just don't put the positive charge on the outside of the brackets and also on the nitrogen. Suppose I have this compound here, or ion here, so let's call this Cn here. So I'm trying to figure out the formal charge on this carbon here. So when I'm trying to figure out the formal charge on this carbon, and if I want to go ahead and draw out this little box here to figure out how many electrons are there on the carbon, you can clearly see there's 2 electrons as lone pairs on the carbon, and there is 3 bonds between, or there's a triple bond between the carbon and nitrogen. So triple bond is going to bring in a total of 6 electrons, and that means you have half of them on the carbon and half of them are on the nitrogen. So carbon having 4 valence electrons, that's coming from the periodic table, and then you figure out how many actual electrons you have on the carbon in this molecule, and it's going to be 2 coming from the lone pair, so those are going to give you 2 here, and then you got 3 coming from these bonds, so it's going to be 5, so that gives you a -1 formal charge. And if you recall, cyanide is indeed 1-, and that 1- is coming from the carbon. So that's how you're going to be calculating the formal charge. It's a good idea to know the valency of some of the common elements you're going to be seeing in the organic chemistry, and obviously carbon being one of them. Carbon is going to be tetravalent, and anytime it's tetravalent, it's going to have no charge on it. So it could have 4 single bonds, or it could have a triple bond or a single bond, or it could have 2 double bonds around, even though it's not the most stable one, but it could still have 2 double bonds around. And as long as it's tetravalent, it's not going to have any formal charge, all right? But if it's not tetravalent, then it's going to have a formal charge depending on the lone pairs. If it doesn't have any lone pair, and if it doesn't have 4 bonds, then it's going to have a positive charge on the carbon. And if it has a lone pair on the carbon, like in the example of cyanide here, and then the 3 bonds, then it's going to have a -1 formal charge. The trivalents are going to be the nitrogen compounds. So usually in a nitrogen compound, you see a total of 3 bonds with a lone pair. And then you could also see maybe just a triple bond, like you've seen in case of cyanide there. And it's always going to have a lone pair. Or you may very well see a double bond and a single bond. So as long as it's trivalent, that's all that really matters. And it's always going to have a lone pair. Now, when you take organic chemistry, and if you see only a triple bond or 3 bonds around nitrogen, and if you don't see the lone pair, it just automatically means there is a lone pair. So you got to be aware of when you can have a lone pair on the nitrogen and other elements such as oxygen. Your oxygen is actually divalent, so you could have 2 single bonds, something like that, and with 2 lone pairs on the oxygen, or you could have just a double bond on the oxygen and the 2 lone pairs on the oxygen. Anytime oxygen does not have 2 bonds, it's going to have a charge on it. Your monovalent is going to be something like hydrogen is monovalent, and your halogens are monovalent as well. So hydrogen doesn't really have any lone pairs on them, but when we talk about halogens, they will have 3 lone pairs. All right, so that's the common representation of the halogens. So halogens could be fluorine, bromine, chlorine, and iodine. So those are the most commonly seen elements you have in organic chemistry. Now, let's talk about electronegativity and the bond polarity. So just in a refresher, how does the electronegativity behaves in the periodic table? So remember, your electronegativity increases when you go from left to right in the periodic table, but when you go down the periodic table, your electronegativity decreases. All right, and when you go from left to right, it holds true up to the halogens. All right, so your noble gas does not have any electronegativities. You stop it at the halogens, and as a result, fluorine is indeed your most electronegative element. All right. The electronegativity values according to the Pauling scale for fluorine is 4.0, but I have not written any of the electronegativity values here, and that's because you want to be focusing more on qualitative polarity instead of the quantitative polarity, and that's what you're going to be seeing for the rest of the organic chemistry. Now, when you do make a bond, suppose I have made a bond between element A and B. So suppose I got in a single bond between A and B. That means there isn't a bonding pair between A and B. Now, this bond pair that's between A and B stays right in the middle, or it stays closer to, suppose, B, or closer to the A. It really depends on the electronegativities. So if your B is more electronegative, then it's going to be the first scenario where the bond pair is going to be closer to the at element B. And if your element A is more electronegative, then it's going to be closer to element A. So that's going to be the unequal distribution of your bonding domain between the two elements, and that really happens whenever there is an electronegativity difference between the two elements. Let's talk about the nonpolar covalent bonds. If you have a electronegativity difference of less than 5, so let's say less than 0.5, or even zero point 0.5, you are looking at a nonpolar covalent bond. Now, obviously, I said earlier, you don't want to be focusing on these differences in the electronegativities quantitatively, but we want to focus on qualitatively. Your nonpolar covalent bonds are going to be the ones that are made between the same type of atoms. For example, in a Cl2, I have a chlorine-chlorine bond, and both of those are going to be having the same electronegativity, so there is no unequal distribution of that bonding domain between the chlorine atoms. So it's that bond is going to stay right in the middle. And when I talk about maybe other elements like O2, H2, Br2, all these diatomic molecules are going to have nonpolar covalent bonds. In addition to that, maybe the most important one is going to be the carbon-hydrogen bond. Obviously, if you see a carbon-carbon bond, that's going to be nonpolar because it's made by the same type of atoms. But when you look at carbon-hydrogen bond, yes, your carbon is a little bit more electronegative than the hydrogen. However, the electronegativity difference is not big enough to create a polar bond. So keep in mind, anytime you see your carbon-hydrogen bond, consider that bond to be nonpolar as well. This is going to come a lot, so you can keep in mind, you remember that. When you talk about polar covalent bonds, your electronegativity difference in terms of numbers kind of stays between 0.5 to 1.5. So again, these numbers are rough ranges and they could change depending on other factors. For the sake of keeping things simple and for the organic chemistry, any other bond you see is going to be considered polar. For example, if I have a carbon-fluorine bond, or if I have a carbon-oxygen bond, or if I have a carbon Br bond, they're all going to be considered polar bonds, even though they may not have an exact difference of electronegativities between the two elements between 0.5 and 1.5. So this is more like qualitative. Just remember, any other bonds you see between the two nonmetals is more or less is going to be considered polar bond. And then if your electronegativity difference is actually greater than 1.5, it's going to be considered an ionic bond. And for the sake of keeping things simple, the ionic bonds in organic chemistry are going to be made between the metals and nonmetals. So for example, the bond between the Na and the OH is going to be an ionic bond because you're literally going to have an Na plus there and an OH minus there. So there isn't a full charge in ionic compounds. I can talk about maybe KCl. So in KCl, you got K plus and Cl minus. And then you don't really have any sort of polarities when you talk about the nonpolar covalent bonds. But when you talk about polar covalent bonds, you will have one element to be more electronegative than the other. So for example, if I look at carbon-oxygen, so when I draw the bond between the carbon and oxygen, it's going to be closer to the oxygen than being closer to the carbon. And as a result, this oxygen is going to get a partial negative charge, and this carbon is going to get a partial positive charge. All right. and you will have a dipole going from the positive to the negative. So this is actually extremely important to be able to identify your polar bonds and to be able to identify your partial positive and partial negative centers in the molecule. So as soon as you figure out there is an electronegativity difference between the two elements and figure out who's more electronegative, whoever is more electronegative is going to be partial negative, and whoever is less electronegative is going to be partial positive. Now, you're not going to be seeing these bonds drawn like that all the time. If you see a carbon-oxygen bond, let's see like this, just to assume this bond that's drawn between the carbon and oxygen, the electrons of that bond are going to be closer to the oxygen, and as a result, this oxygen is going to have a partial negative charge, and this carbon is going to have a partial positive charge, and then there is going to be a dipole going from the positive center to the negative center. And that's all you really gotta worry about. If I take another example, I can talk about maybe carbon and chlorine here. So even in carbon-chlorine, chlorine being on the right side, it's going to be more electronegative than the carbon, and as a result, it's going to have a partial negative charge, and carbon's going to have a partial positive charge. So you have a dipole going from the carbon to the chlorine. So that's how you want to draw the polar bonds, and we'll talk about how the polar bonds affect the polarity of the molecule overall. So let's talk about that now. So overall polarity of the compounds really depends on what type of bonds you're dealing with. So suppose if you have only nonpolar bonds, then you're always going to have a nonpolar compound. So there's no net dipole in the molecule in that case. You can talk about examples like Br2, Cl2, or even like CH4 or C2H6, or even like C8H18. All they really have is just nonpolar bonds. And if you have only nonpolar bonds, they're always going to make nonpolar compounds overall because there's no net dipole moments. Now, what about cases like when you have a polar bond? If you have a polar bond, that does not always mean that you're going to have a polar compound. You got to look for the symmetry of the compound. If there isn't a plane of symmetry in the molecule, then there is a good chance there will not be any net dipole, and as a result, your molecule will be nonpolar. Let me take a very good example. We talked about CO2 earlier, and we have drawn the Lewis dot structure of CO2. And when I look at this carbon-oxygen bond, remember oxygen is more electronegative than the carbon, and as a result, you're going to have one dipole going this way, and you're going to have another dipole going this way. I can also write down carbon being less electronegative, so it's going to have a partial positive, oxygen is going to have a partial negative, and this oxygen is also going to have a partial negative. So you can clearly see here you have two dipoles being created by these two bonds here, but they are opposite to one another. So since they are opposite to one another, they cancel one another out. There is actually a symmetry in the molecule. So if I draw a line here, then the left side of the molecule is the same as the right side of the molecule, and I can clearly draw the line horizontal as well, where the top of the molecule is the same as the bottom of the molecule. So whenever you have a plane of symmetries or your molecule is symmetrical, even after having your polar bonds, your molecule would be overall nonpolar. What about taking another example? So stuff like CCl4. So when I draw the Lewis dot structure for the CCl4, it will have carbon-chlorine bond, which are going to be polar bonds. But since you have this molecule to be symmetrical, all those dipole will cancel out one another, and there's not going to be any net dipole. So just like in case of carbon dioxide, there was no net dipole. Similarly, in case of this CCl4, there is not going to be any net dipole because they all cancel one another out. So no net dipole in this particular case as well. Just because you have polar bonds, that does not necessarily mean your molecule is also going to be polar. If all the dipoles created by individual bonds are canceled, then you're not going to have any net dipole. And if there's no net dipole, your molecule is going to be overall nonpolar. What about if you have an unsymmetrical molecule? All right, so things like water is one of them. Because when you have drawn the water, this is how it looked like. Since it's a bent in shape, you can clearly see that oxygen is going to be more electronegative, so it's going to have a partial negative charge. Hydrogen is going to be partially positive. And when I draw the dipoles, you're going to have one dipole going this way from the hydrogen to the oxygen, and then you'll have another dipole going this way. And they're not totally opposite to one another. Maybe a part of those dipoles cancel one another out, but there's still going to be a big chunk of dipoles going to the top. So sometimes they do ask you to draw the direction of the net dipole. So this is how the net dipole is going. It's going to be going toward the top of the molecule. So since there is a net dipole, you will have this molecule to be polar. What about something like NH3? So nitrogen being more electronegative, it's going to be partial negative charge. Hydrogen is going to be partial positive. And you can clearly see there is going to be a dipole going toward the center there. And maybe some of the dipoles cancel one another out, but not all of them. And as a result, this will be a polar molecule. And there's really not any way you can have the symmetry on this molecule. If I draw a vertical line, or maybe like let's say if I draw a horizontal line there, then the top of the molecule is not the same as the bottom of the molecule. And as long as you have polar bonds, no plane of symmetry, you will have an net dipole in the molecule, and overall that molecule is going to be polar. So that's how you're going to be looking at the polarity of the molecules. Let's talk about what are going to be the polarities of these molecules. So sometimes you could have both ends. You could have the polar side and the nonpolar side. So you can clearly see here, this left side, all you really have is a carbon-carbon or carbon-hydrogen bond. So this side is actually going to be nonpolar. But then you can also see this carbon-oxygen bond, oxygen being more electronegative, is going to have a partial negative charge, and carbon being less electronegative is going to have partial positive charge. So you will have a dipole going toward the oxygen. So that's going to be your polar side. So that's another thing you want to be able to identify, that in a given molecule you could have a nonpolar side and a polar side. Another factor I do want to point in here, the oxygen does not have the lone pairs shown here. Now when you do take organic chemistry, if you see oxygen having only 2 bonds and no lone pairs, it just automatically means there are actually 2 lone pairs. So that's, you will see that oxygen drawn just with 2 bonds and no lone pairs on it, but you just have to know by now that there are 2 lone pairs on that oxygen at that particular time. So you do have the polar and the nonpolar. Be able to draw your partial positives and partial negatives on the given molecule. We can clearly see this next one here. Kind of similar. In the next one, you're going to have this nonpolar side, because all you really got is the carbon-hydrogen bonds, which are nonpolar, or carbon-carbon bond, which is also nonpolar. But when you look at this next side here, you got the OH and the CO. So those are going to be your polar bonds. And if I be a little bit clear here, your oxygen is going to be a bent molecule, so you're going to have this bond a little bit tilted. So that's how usually it's drawn. And then you can clearly say oxygen is going to be more electronegative. It's going to have partial negative charge. This hydrogen is going to have a partial positive charge. That carbon is also going to have a partial positive charge. So you have a dipole going from the carbon to the oxygen, and then you also have a dipole going from the hydrogen to the oxygen. Okay, what about this next one here? Clearly, we got this left side and this right side carbon-hydrogen bonds, so those are going to be nonpolar sites. But then you can clearly, you have this nitrogen at the center. Nitrogen is going to be more electronegative than both the hydrogen and the carbon. You really have the lone pair on the nitrogen, and that's because when you take organic, and if you see 3 bonds on the nitrogen, that means there is going to be a lone pair on that nitrogen. Nitrogen being more electronegative, it's going to have a partial negative charge. These carbons going to have a partial positive charge. So does this hydrogen. So you'll have these dipoles going this way. So those are the story with those bigger molecules. In bigger molecules, you could very well have a nonpolar site, but then you can also very well have the polar site. And to be honest, the polar site is where a lot of these reactions are going to take place, because if you have the polarity in the bond, which literally means you can break that bond, that's when the chemical reaction, that's where your chemical reaction is going to take place. So that's why it's extremely important to be able to figure out your partial positives and partial negative sites in the given molecules based on your electronegativities. Let's talk about atomic orbitals. Now, when you're talking about an element, and we have talked about electronic configurations and their subshells and the orbitals, what we're really doing in that particular case, we're talking about the probability of locating the electrons around the nucleus. And usually in those particular orbitals, when we talk about it's 1s orbitals or 2p orbital or 3px orbital, in that particular region, the probability of finding the electron is going to be very high, almost 90 to 95%. And then, the rest of that small amount of probability would be outside that orbitals. So the very first orbital you have seen is the 1s orbital. So remember, your s orbitals are sphere in shape, so these are going to be your s orbitals. And these are going to be spheres. And this first one is the 1s, the second one is the 2s. So the difference between the 1s and the 2s is just barely the size between those two, and also how many nodes you can have. So in 1s, there is no node. So when you're trying to find the number of nodes, it's always going to be your principal quantum number minus 1. So for 1s, there is 0 node. And then in 2s, there is going to be 1 node. So I have drawn that node with this pink color here that's around this nucleus. What node really means? Node means you have a 0 probability of finding the electron in that particular region. So this particular one is going to be called a radial node. The radial nodes are usually inside the orbitals, and then you also have so-called angular nodes. The angular nodes are going to be usually not inside the orbitals, but they're going to be in the surrounding region somewhere. If I take an example of these next 3 sets here, those are your p orbitals. I can call this py and call this px, and I call this pz. So those are the 3 p orbitals you have. And you have those 2 lobes on this p orbitals, kind of in a dumbbell shape. You have the positive side on the top, so you call this positive psi, and then on the bottom you call that negative psi, and then in between there, this region, that's where you're going to have another node where the probability of finding the electron is going to be 0. You have 2 sites of these lobes where you just randomly call the top one positive and the bottom one negative. That doesn't necessarily mean you have negative probability of finding the electrons on the bottom. It's just the orientation. So you have the positive side and the negative side. Just like in a wave, you have the crest, which are the positive sides, and the troughs, which are the negative sides. Same story, you have the positive side and the negative side. If you have to figure out the probability of finding the electron in a given region, it's measured by psi square. All right, so psi square, whether you look at the top or the bottom, is going to be the same. However, the psi square, when you're looking at the node, is going to be 0. And that literally means the probability of finding the electron at that particular node is going to be 0. And this particular node is going to be called an angular node. So when you find the total number of nodes by using this formula, which is the principal quantum number minus 1, that's going to be the sum of your radial nodes and angular nodes. The angular nodes is usually going to be given by the value of L. So remember, the value of L for p orbitals is going to be 1, so that's why there is one angular node. For the d subshell, the value of L is 2, so that gives you 2 angular nodes, and the rest of the nodes would be radial node, depending on how many total nodes you have in the given molecule. Let's talk about the arrangement of these subshells or these orbitals. And that's called an Appel principle, which is just the arrangement of the subshells in order of increasing energy. Or another way of saying, this is how you write the electronic configuration. So I'm not going to be focusing on like a really big electronic configurations, but just maybe up to third row. So we have 1s, and then you have 2s. Then after that you have 2p, and then you got 3s, 3p, and then you have 4s. After 4s, your 3d starts, and then you have 4p. Up to this point, it's usually good enough because that's all you're really going to see. Your carbon in your second row elements is mainly kind of relying right there. If you go on to the third row elements, then you're talking about this 3s and 3p, and in organic chemistry you barely go over 3 rows. When you're writing the electronic configuration, suppose I'm focusing on the nitrogen. Nitrogen has an atomic number of 7, and its electronic configuration is going to be 1s2, 2s2, and 2p3. Now, when I'm putting those electrons in those orbitals, so you have one orbital in 1s, one orbital in 2s as well, but then I have 3 orbitals in 2p. So remember, that's why we have 3 drawings for those p orbitals on the top there. So your 1s is going to have 2 electrons, your 2s is going to have 2 electrons, and then your 2p is going to have 3 electrons. So the Hund's rule says if you have orbitals of same energy, you must have filled those before you start pairing them up. So this 2p, since it has 3 electrons, I want to half fill each of those orbitals before I start pairing them up. Let's talk about electronic configuration for the carbon. So carbon is going to have 6 electrons, because that's the atomic number for carbon, and it's going to be 1s2, 2s2, 2p2, and then we can clearly focus on only the valence electrons. And when I draw the energy diagram for this, or the energy arrangement for these orbitals, so your 1s is going to be on the bottom, and then you have 2s, and then for the 2p, since I'm going to have 3 orbitals, I'm going to draw 3 of those lines here. So the 1s is going to be 2 electrons. Your 2s is also going to be 2 electrons, and then your 2p, since it has 3 orbitals and all of them has the same energy, and the same energy orbitals are also called the degenerate orbitals, and we will place 1 electron in each before we start filling those up. So if this is true, based on this arrangement, carbon should be able to make only 2 bonds, because the bonds are made by the half-filled orbitals. However, that doesn't really happen. Carbon is tetravalent and it's able to make 4 bonds. In order for carbon to be able to make 4 bonds, one of the electrons kind of get excited, not really excited, but it kind of gets moved from the 2s onto this 2p, and when that happens, you get a different set of arrangements. So now if I just copy this on here, so when this gets excited, I would have one of these electrons from the 2s moved onto the 2p. So now you got 4 orbitals that are half-filled, and now you can explain how carbon is going to be making 4 bonds. In addition to that, there is going to be something called an hybridization. So these s orbital and these p orbitals going to hybridize, where they make a set of 4 orbitals now. So remember, this set of 4 orbitals is going to have the energy in between the 2s and the 2p. Not drawn on scale, but just qualitatively, if you look, the 2p are higher in energy than the 2s, and when you mix those up, or when you hybridize this 2s and 2p, they will have energy in between the 2s and the 2p sets. And then all of a sudden I got these 4 orbitals that are half-filled, and they are going to be an sp3 hybrid orbitals. Now, your electron movement does take place, but that doesn't necessarily mean you're going to be using all these 4 orbitals in the hybridization. You may very well use only 3, and in that case it's going to be called an sp2, and then your last orbital is going to left unhybridized with still 1 electron in there, and that's going to be capable of making so-called an pi bond. Based on this hybridization, you can explain why the carbon is actually going to be tetravalent, why it's able to make 4 bonds. Now, the other important note I do want to make here, remember your s orbital is sphere, so when I have this s orbital, so this is going to be 2s, and let me take one of the 2p orbitals there, which is going to be in a dumbbell shape. So when you hybridize those, what's going to happen? It's like saying, like, when you mix 2 colors, what happened to the resulting colors? Or when you mix 2 shapes, what's going to happen to the resulting shape? It's not going to be any of the original ones. And same thing happens here. You're not going to have the sphere, or you're not going to have a dumbbell, but your sp hybrid orbitals is going to be looking something like this. You'll have like a half a dumbbell, and you'll have a little bit of circle on the other side. This arrangement for these sp hybrid orbitals is really good for the proper orientation and proper overlapping of the atomic orbitals. Now, if I want to take an example of maybe CH4, so in CH4, I know carbon makes 4 bonds, so it's going to be an sp3 hybrid carbon. And since it's going to be an sp3 hybrid carbon, so suppose this is my carbon right there. So I'm going to have 4 orbitals that are going to be hybridized. So I'm going to be drawing those 4 orbitals first. Okay, and then remember your hydrogen, which has an atomic number of 1. It's going to be 1s1. So what it really has is the sphere. So it's got 1 orbital that's sphere in shape. So if I change the color of that, the 1 electron from this hydrogen and 1 electron from each of those 4 hybridized orbital of carbons, they're going to overlap with one another. So they're going to be running so-called an end-to-end overlapping, and that's where you're going to be making this sigma bond. So that's going to be called the sharing of those electrons. So this carbon is an sp3 carbon. And sometimes they ask you questions like, okay, what particular orbital is making the bond between the carbon and hydrogen? Then you're going to be calling this sp3 hybrid orbital, because you don't really know which particular one, but it's just going to be an sp3 hybrid orbital, and 1s orbital making the bond between those 2 atoms. So the sp3 hybrid orbital obviously coming from the carbon, and 1s orbital obviously coming from the hydrogen, that are the one that's making the bond in there. How do you really recognize if you have a double bond or a triple bond? Let's talk about that. I have some of these examples here. So this particular carbon on the left side here, it's got 4 bonds around it, so it's going to be an sp3. sp3 carbons are always going to be, not always going to be tetrahedral, but mostly they're going to be tetrahedral as long as there's no lone pair on them. This particular one, you got it's going to be an sp3 again. This next carbon right there, it's got only 3 electron domains around, or another way of saying there is one double bond. So this pi bond that's being created between the carbon and oxygen, it's a result of an unhybridized orbital. So you still have that shift of the electrons from the 2s to the 2p, but one of the p orbitals stays unhybridized. So as a result, this carbon is actually going to be an sp2. What about that oxygen there? Well, when I focus on the oxygen, and if I count the total number of electron domains on the oxygen, I know there is 2 lone pairs on the oxygen, even though they're not shown there, but by now you should know that oxygen is going to have 2 lone pairs if there's no charge on it, and if there are 2 bonds onto the oxygen. And since there's 2 lone pairs on that oxygen, and 1 electron domain, so this double bond count as 1 electron domain because the other bond on this double bond, which is going to be the pi bond, is coming from the unhybridized orbital. So this oxygen is also going to be an sp2. And then you don't really focus on the hydrogens in terms of the hybridization. What about this next set here? This carbon, again, it's got 4 electron domains around all single bonds. It's going to be sp3. This second one is also sp3. What about this oxygen here? Well, it's got 4 electron domains around it because you got 2 single bonds and then you got 2 lone pairs. And your lone pairs count in the hybridization as long as they're not delocalized. So I want to say that again. If they are delocalized, then you will not count those in the sp or in the hybridization. And I'll talk about the localized and delocalized lone pair in a separate video. But here, just assume all these are localized. Okay, what about this next one here? So we got a carbon that's got 4 bonds around it, so it's going to be an sp3. What about this next carbon here? Well, now all of a sudden you have a triple bond here. So when you have a triple bond, your triple bond has 2 pi bonds in there. So remember, your pi bonds are going to be made by unhybridized orbital. So another way of saying, you got 2 unhybridized orbitals on this carbon, and if there is 2 unhybridized orbital on the carbon, you must have 2 unhybridized orbitals on the nitrogen as well, so that they can do so-called a side-wise overlapping to make the pi bond. And as a result, anytime you have a carbon with a triple bond, it's going to be an sp hybrid, where it's going to be linear in shape and the bond angle is going to be 180. This nitrogen, you see a triple bond, which is going to count it as 1 electron domain, but then also keep in mind there is a lone pair on the nitrogen as well anytime it's making 3 bonds. As a result, it's going to have 2 electron domains being used up in the hybridization, so that's going to be an sp hybrid as well. We'll talk about how this lone pair really comes along. It's a part of non-bonding molecular orbital, so we'll talk about that in a minute, but for right now, just know if you have a lone pair, it could be a part of your hybridization as long as it's not delocalized. Okay, what about this next set here? So we got this carbon, so we got a double bond and then 2 single bonds, so there's a total of 3 orbitals being hybridized, so it's going to be an sp2. What about this carbon here? That's going to be an sp2 as well. Well, seems like they're all going to be sp2 carbons, so is this one. And this oxygen is also going to be an sp2 because remember there is 2 lone pairs on that oxygen and there isn't a pi bond. Now, the other type of question you would see here, let's just focus on this part here, they could very well ask you what kind of orbitals are making the pi bond between the carbon and the oxygen there. So you have an unhybridized, so we'll say unhybridized p orbital in carbon and unhybridized p orbital in oxygen that are overlapping to make a pi bond. To summarize all these things, I do want to mention that if you have a carbon, or if you have a single bond, It doesn't really matter whether you have a carbon-carbon single bond or like nitrogen-nitrogen single bond, or you have a sulfur-sulfur single bond. As long as you have a single bond, and we'll just take an example of carbon here, then you're going to have one sigma bond. The symbol for sigma is going to be this Greek letter called sigma. And then if you have a double bond, so in case of a double bond, you will have carbon-carbon double bond. So you'll have one sigma and you will have one pi bond there. And if it's a triple bond, you'll have one sigma bond and two pi bonds. So sometimes they do ask you questions like count how many sigma and pi bonds are there in a particular molecule. Like if I go back, and we change the color there, and if I look at maybe this molecule here, and if I'm counting the number of sigma bonds there, so it's going to be 1, 2, 3, 4. And in triple bond, you're going to have one sigma bond, so it's going to be 5. So I got 5 sigma bonds. And then how many pi bonds you're going to have? There's no pi bond on the single bonds, but since you have a triple bond there, that's going to be 2 pi bonds in there. So before we move on to the next topic, I do want you to guys do hybridization of carbon in CO2. So remember, the CO2 has a double bond of carbons on both sides with the oxygen. What's the hybridization going to be here? So remember, the easier way to look at it, how many electron domains you have. So you got a double bond on the left side, double bond on the right side, and you need only 2 electron domains. So since you need only 2 electron domains, you need only 2 hybrid orbitals to do the hybridization there. So that means it's going to be an sp hybrid orbital. Just very similar to you would see in a triple bond, because in 2 double bonds you will have a total of 2 pi bonds. And this oxygen right there is going to be an sp2, and this oxygen is also going to be an sp2 hybridization. And when you talk about what type of bonds or what type of orbitals are making those bonds, you can talk about the sigma bond between the carbon and oxygen is going to be made between sp hybrid orbital of carbon and the sp2 hybrid orbital of the oxygen. So this is coming from the carbon and that's coming from the oxygen. So that's another type of question you will be seeing in there. Let's talk about the bond length and the bond strength. I'm not going to be talking about the numbers, but just qualitatively, you want to be able to figure out who's going to be a shorter bond and who's going to be a longer bond. And if you have a shorter bond, it's usually harder to break, or it has an extra strength. Now, in this first example, I have 2 carbons that are single bonded with one another. So both of these carbons going to have an sp3 hybridization. And when you look at this second set there, both of those carbons going to have an sp2. And in the next set here, both of those going to have an sp hybridization. Now also worry about the percent s character and p character in those different hybridization. So if you have sp3, we're looking at 25% s character in that hybrid orbital and 75% p character in the hybrid orbital. But when I'm looking at the sp2, it's going to have 33.3% s character, and it's going to have 67, let's say 67.6 to make a total of 100 roughly, p character. So you have more p character. You have more p character in the sp3 hybrid than in the sp2 hybrid. But when I'm looking at sp, you have 50-50. You got 50% s and you got 50% p. So another way of looking at it, your s orbitals are closer to the nucleus. The more s character you have, the closer the electron's going to be toward the nucleus, and as a result your bond's going to be shorter. So that's one way of looking at it. The other way of looking at it, there is going to be 1 pi bond in the double bond, and there's going to be 2 pi bonds in the triple bond. So those pi bonds, since they do the sidewise overlapping, they also bring those atoms closer to one another. In terms of the bond length, your single bond are going to be the longest, and your triple bond is going to be the shortest. And obviously your double bond kind of stays in between in that case. And then in terms of the strength or the bond energy, your triple bond is going to have the highest bond energy, or you can also say they are going to be the strongest because they will need more energy to break. And then your single bond is going to have the lowest bond energy. And they are going to be the weakest to break. And when you look at triple bond, we're looking at all together compared to the single bond. They're not individual bonds in the triple bond. Okay, so that's how you're going to be looking at the strength of these bonds. And sometimes you will have a bond length between the single bond and the double bond, and that's when you look at the resonance. Like that means a typical bond does not have a full single bond character and also does not have a full double bond character, but it's in between, and that's when you're going to have the bond length of that particular bond in between the single and double bond. Okay, so that we'll talk about that when I have a separate video for the resonance. But here, just generally know the strength and know the S and P characters of different types of bonds and hybridization. Let's talk about the overlapping of atomic orbitals. Remember, we talked about electrons being in the atomic orbitals when you talk about elements, but when you do make the compounds or the molecules, how would you really talk about those electrons? Like, where would they going to be? Will they still be in the atomic orbitals, or will they be somewhere else? So it turns out when you combine those atomic orbitals, you will have so-called molecular orbitals being made, and you will have those electrons in the molecular orbitals in that case. So there's actually two theories that talks about overlapping of atomic orbitals. The first one is called a valence bond theory, and the second one is called a molecular orbital theory, or in a short form is the MO theory. The valence bond theory is a little bit easier to talk about, or a little bit easier to understand, so we'll talk about that first briefly, and then we'll briefly talk about the molecular orbital. And I'm not going to be talking too many details in those theories. I'm going to be talking about only the stuff that you will be needing in organic chemistry. In valence bond theory, what they say, you treat the electrons as a wave. So if you have taken physics, the wave is going to be anything that has the repetition motion. And you can combine the waves two different ways. You can do so-called a constructive interference, or you can combine the two waves. You call those destructive interference. So in a constructive interference, means if you have the positive end of one wave, so let's suppose this is the positive end of one wave, and the second wave's positive end, if they combine with one another, you're going to make a wave that's going to have a higher amplitude. So it's like in a superposition. They're going to get added up. Your amplitude increases. So when you do make a sigma bond, there is actually a constructive interference or constructive combination of those two atomic orbitals. So if I talk about hydrogen molecule, so in hydrogen molecule you got two hydrogen atoms connected with single bond with one another, and each hydrogen atom is going to have a 1s orbital, so 1s1, 1s1. So when I combine those 1s orbitals with one another, they're going to be combining together in the form of constructive interference. What that really means, the electron density of the 1s orbital of one hydrogen atom and the 1s orbital of the second hydrogen atom, they meet in phase so that they will have so-called a constructive interference, and your amplitude is going to go up. So if I redraw that, so just kind of show the amplitude kind of going up in the middle. So that's what makes it a constructive interference. So this is what makes really a sigma bond. So a sigma bond, your electron density is going to be right on the axis. So when I draw in the form of a bond, those two electrons are going to be right on that particular axis of the bond that we have drawn in that case. However, if those two atomic orbitals meet with one another according to destructive interference, which means you have the positive side of one electron or one wave and the negative side of the other wave, when they meet together, those amplitudes going to get canceled out, and then you may get just a flat line there, all right, with no amplitude. And when you get a flat line there, you also create so-called an anode. That's where the probability of finding the electron is going to be 0 there. So that's your first theory, just focusing on the constructive and destructive interference of the atomic orbitals, creating a sigma bond if you do constructive interference, and if you do a destructive interference, you're creating a node there where the probability of finding the electron is almost going to be 0, or it's literally going to be 0. The second theory is more like in a mathematical way of combining the atomic orbitals. It says mathematically, if you have a total of, let's say, 4 atomic orbitals coming from your atoms, when they do combine together, they will make a total of 4 molecular orbitals. And then it also talks about how in one atomic orbitals you can have a maximum of 2 electrons, so 2 max electrons in one atomic orbital. That theory still stays the same. You can place 2 max electrons in one molecular orbital with opposite spin. So one electron is going to be going up and the other electron is going to be going down. You create 3 different types of molecular orbitals, possibly. Like you will see 2 of them all the time, and the third one is going to be there sometimes, and sometimes it may not be there, depending on the type of bonds you're making in there. So the first molecular orbital is called a bonding molecular orbital. The bonding molecular orbital comes from the constructive overlap of atomic orbitals. So that kind of goes back to the valence bond theory where it talks about the constructive and destructive interference. If you do overlap 2 atomic orbitals with constructive interference, you will make a bonding molecular orbital. And another important thing about bonding molecular orbital, they will have energy lower than their parent atomic orbitals. That's an important thing you want to make sure you know. And then the second, if you do have those atomic orbitals combining destructively interference, then you will have made an anti-bonding molecular orbital, and that anti-bonding molecular orbital will have higher energy than your parent atomic orbital. And I'll give you an example in a minute. And then occasionally you may see something called non-bonding molecular orbitals. Now, non-bonding molecular orbitals are actually going to be equivalent to the lone pairs that you have seen in the electron dot structures, and they usually have the same energy as that of atomic orbitals. So if you recall ammonia or NH3, and I said I'll come back to that, this lone pair that's on the nitrogen is coming from the non-bonding molecular orbital. So there is one non-bonding molecular orbital when you're looking at the MO diagram for the NH3. And then if I talk about H2O, so in water you have 2 lone pairs, so you can literally say that there are going to be 2 non-bonding molecular orbitals in water. So the short term for the bonding molecular orbitals you may see is BMO, that's bonding molecular orbitals. For the antibonding is going to be ABMO, so it's anti-bonding molecular orbital. For the non-bonding is going to be NBMO, so non-bonding molecular orbitals. Now, if I draw a hydrogen atom, or hydrogen molecule rather, So suppose I got two hydrogen atoms. One is right there, and the other one is right there. And I know the hydrogen atom's electronic configuration is going to be 1s1. So I have one at 1s orbital in each of those hydrogen atoms. And they're going to have the same energy to begin with. So you want to make sure you draw both of those at the same line. And then I got one electron on each of those. So when you do combine them together, so there's going to be the total number of your atomic orbitals are going to be equal to the total number of your molecular orbitals that we talked about earlier. So if you're combining two atomic orbitals, you must make two molecular orbitals. And when you do make molecular orbitals, you also always going to have your anti-bonding molecular orbitals to be equal to your bonding molecular orbital. So if I create one bonding molecular orbital, you will also create one anti-bonding molecular orbital, which kind of makes sense because remember, you can either combine your atomic orbitals with constructive interference or destructive interference. So if you combine with constructive interference, you make bonding molecular orbital, and if you combine with destructive interference, you make anti-bonding molecular orbital. So if I do combine those together, so you'll have one possibility where your bonding molecular orbital is going to be lower in energy than your parent atomic orbitals, and then your anti-bonding molecular orbital is going to be higher in energy than your parent atomic orbitals. Okay, so this is going to be the anti-bonding molecular orbital. Now, this bond, when you're filling in the electrons, the theory of filling the lower energy orbitals still stays the same. So you're going to be filling in your bonding molecular orbitals first, and you have a total of 2 electrons coming from the 1s, and then I'm going to go ahead and put both of those electrons in the bonding molecular orbitals, and in that case, your anti-bonding molecular orbital really doesn't get anything. So that's all you're really going to have in this particular scenario. So be able to identify where your bonding molecular orbitals and your anti-bonding molecular orbitals are. And if you had a non-bonding molecular orbital, for example, it would have been at the same level where your atomic orbitals are. So I'm not going to draw that here because it does not have any, but if it did have one, then it would have been on that pink line there. Now, what's the take-home message here? The take-home message for these molecular orbital theory is be able to identify something called a HOMO and a LUMO. So your HOMO is going to be the highest occupied molecular orbital, and your LUMO is going to be the lowest unoccupied molecular orbital. Now that doesn't really have to do directly anything with bonding and anti-bonding. Sometimes you may have your anti-bonding molecular orbital to be the highest occupied molecular orbital. So it's just a way of looking at it. So when I look at this particular one, this particular hydrogen atom here, hydrogen molecule here, your highest occupied molecular orbital is going to be, let me change the color there, is going to be this guy right there. So that's going to be called the HOMO. And your lowest unoccupied molecular orbital is going to be this top one. And it just turns out you only have 2 in there. So one is going to be HOMO and the other one is going to be LUMO. But later on, when you start talking about Diels-Alder's reaction in a second semester organic chemistry, this is where you're going to be talking a lot about these HOMOs and LUMOs. So you want to make sure you know the definition of a HOMO and a LUMO. So a HOMO is the highest occupied molecular orbital where you're going to have the electrons, and your LUMO is going to be the lowest orbital that does not have the electrons in there. Okay, so those are your 2 theories about making the molecules after overlapping the atomic orbitals. So we kept things very basic because I didn't want to really go into too many details, and that's all you really need to know about these valence bond theory and the MO theory when you go in the organic. And like I said, these bonding, anti-bonding, and then these HOMOs and LUMOs will come back at some point when you start talking about the second semester organic, and more specifically the Diels-Alers reaction. All right, so this is all you really need to know about your basic Gen Chem. If you have any questions, or if you want me to go over any other concepts, then feel free to leave any comments in the section.